Okay, so actually, this is section 2.2, polynomial functions. All right, and I start out here with j of x, not a letter you see all the time, but still a letter you can use. J of x is equal to quantity 2x plus 1 closed quantity squared times quantity 1 minus x closed quantity cubed times quantity x squared plus 1 closed quantity squared times quantity 3x minus 5 closed quantity. When I graph it in Desmos, it looks like this. This is the shape or the form that the graph takes. Now, some of the numbers that you see where interesting things are happening actually correspond to some numbers that will make this polynomial function 0. Now, this is in factored form as opposed to being written out as instead of multiplying all of these out and then combining like terms, we've got it broken up into factors. Why do we want to do that? Because if you break it up into factors, it's a whole lot easier to see the zeros. What's the order? What's in parentheses matter? So like this 1 minus x as opposed to x minus 1. The order would matter if it's subtraction. If it's addition, it doesn't. You can swap these around. This could go the first one. This could be the last one. We don't typically write these in descending order or ascending order, so no, I don't know which one comes first, which one comes second, doesn't matter. The only one of the this 1 minus x is going to needs to be always written as either 1 minus x or negative x plus 1, and then 3x minus 5 needs to be 3x minus 5. But the rest of them can be swapped around. So, oh yeah, that'd be fine. That would be absolutely fine. Yeah, if you wanted to write it in descending order and put that factor out here, that's absolutely fine because multiplication is commutative, right? A times B is the same thing as B times A. So yeah, you can stick that out front if you want. But let's take a look at the factors, right? If I want a product of multiple factors to be 0, all I have to do is get one of them to be 0, right? If I have, like, so for this case, I have 1, 2, 3, I have 4 factors in this equation, j of x, right? If I wanted j of x to be 0, all I have to do is make one of these factors 0. And if I can make one of the factors 0, when I plug it in, when I plug in that value for x, that factor is going to go to 0, and 0 times, I don't care what else is in the function, it's 0 times it. 0 times whatever, times whatever, times whatever is 0. So let's list the factors, and let's see if we can do a little manipulation here. So what are my factors? The factors are 2x plus 1 squared. I'll tell you what. Let's just go ahead and scoot that over. All right. Next, 1 minus x cubed. Two x plus 1 squared. And last one, 3x minus 5. All right, so I've got factors. So, and it said the reason that you like to have the factors is we've been interested in this before. Yes, it does, Andrew. So if I square or cube, it does change the behavior. All right. So what are the zeros? So the zeros are the values of x that make each factor equal to 0. So I just take what's inside the parentheses, 2x plus 1. I set it equal to 0 and I solve. Subtract 1 from both sides. 2x is equal to negative 1. Divide both sides by 2. And x equals negative 1/2. All right. Negative 1/2 is negative 5/10, right? Well, there's negative 5/10 right there. And look at where I'm at. I'm on the x-axis. And what is y? Y is equal to 0. So each one of these, if I have a solution to these, take the factor, set it equal to 0, I'm going to find myself at an x-intercept. All right, so what's the other 0? So take 1 minus x, set it equal to 0, and solve. Tell you what, let's see how everybody feels about this. Everything with an x on one side, everything without on the other. This x is currently subtracted, so I'm going to add it to both sides. And I'm going to find x is equal to, or excuse me, 1 is equal to x, which is the same thing as x is equal to 1. Okay? X squared plus 1. Take that, set it equal to 0 and solve. Subtract 1 from both sides. X squared is negative 1. Square root. X is equal to the positive and negative square root of negative 1, which is I. Okay, so whenever you do these, if you get a factor and you end up with an imaginary 0, it means that you have to square root of negative 1 is I. So whenever you run into this, whenever your solution comes out to be complex, it means that it doesn't show up on this graph, because this graph, this is x values and y values. There's no imaginary dimension on here. So whenever you run into one of these, this means, yes, there is a number you can plug in to make this 0. It's just imaginary. And then the last one over there, 3x minus 5. Set it equal to 0 and solve. Add 5 to both sides. Divide by 3. And we're going to find out x is 5/3. All right. So I have found the zeros, if they have them. Next, I'm going to find the corresponding x-intercepts. Okay, what are they? Well, that one is negative 1/2, 0, right? Because when x is negative 1/2, y is 0. And this one, whenever x is 1, y is 0, because that's right there. There's the negative 1/2. There's the 1. This one, not applicable because this one does not have a real 0. And then lastly, 5/3, 0. And there it sits. Okay. So finding those zeros lets me find my x-intercepts. Okay. Now, what about the powers? Okay, Andrew already alluded to this. Something called P-L-I-C-I-T-I-E-S, multiplicities. Okay, let's not even pretend like that can be read. Okay, we're going to do multiplicities. Okay, what I want you to do here is just find or tell me what is the power factor is raised to. All right, so my first one is 2x plus 1 squared. All right, so that's to the second power. The next one, 1 minus x is to the third power. Next one is to the second power. And then the last one, if there's no power up here, what's it understood to be? 1. Great. Now, what do you notice about the behavior? Yeah, ignore this one. It does have a multiplicity of 2, but it's imaginary. So take a look over here. My first root, my first 0 is at negative 1/2 0. Its multiplicity is 2, and the graph comes up, it touches, and then it goes back down. The next 0 I run into is 1 0, and when I get there, I hit and I actually cross. Okay, so I go from below to above, and then the last one, I come down, I get it, and then I cross again. Well, so these last two, that's not wrong. The last two actually have a similar behavior, whereas the first one is completely different from the others. Can anybody see what do 3 and 1 have in common that isn't true of 2? What kind of number is 2 and what kind of number is 3? How are they different? Any thoughts? Even and odd, exactly. So my first 0 is even. The next one is odd. I'm going to ignore the imaginary one for a second. And then this last one is odd. That determines the behavior when it comes to zeros. All right. So since I have, just drag this down even slower. All right, so whenever I have a power that is even, my behavior is going to be to touch. Whenever the power is odd, my behavior is going to be to cross. All right. So whenever I take my polynomial, I get it down into its factored form, I'm going to check the multiplicities, and if the 0 at negative 1/2 0 has an even multiplicity, when I go to sketch this graph, it's going to touch. All right. And then if I have one that's odd, it's going to cross. All right. So we have introduced zeros. We know how to find our x-intercepts, which we've run into before. And now I've introduced multiplicities and then their behavior. So the only thing left is for you to take this original function and we got to pick up just a couple more attributes. All right. So here's the function. Now, the degree, oh, and last thing on multiplicities, notice that I don't care how odd or how even a number is, the behavior is just still going to be touch and cross. The higher the power, I think it's just going to get really tight. If it's going to go up, touch and come down, it's just going to, that parabola is going to get closer and closer together. And then if it's odd, it's probably going to just, it's just going to be it's going to grow a lot faster. So it'll, once it crosses, it'll probably speed up on, it'll get steep and steep. But anyway, there is my function. The other pieces of information I need if I want to talk about my polynomial function is I'd like to talk about end behavior. Okay? So if this is my polynomial, it's the end behavior. That is controlled by the leading term. Okay, why is that? Okay, well, let's take something super easy first, and then let's see if we can expound on it. All right, so take a look at I can tell it is working hard in the background. All right, so I got y equals x squared. That's my basic parabola, right? Now, when I add 3x, right, my parabola got a little bit wider, and the vertex moved down. We'll say I subtract 2, that shifts the parabola down 2 units. I can add whatever I want to onto the end of this. The end behavior is what happens as x goes off toward negative infinity and what happens as x goes off toward positive infinity. Okay, so when I look at this parabola, this first term is squared. The second term is multiplied by 3, and then the last term is a constant. So I want you to think about as x starts to grow, right? When x is 1 or x is 2 or x is 3, those 3 terms, they don't have equal weight, but they're pretty close together. But when x is 50 or 1,000 or 1,000,000, think about what's happening here. That would be 1,000,000 squared plus 3 times 1,000,000 minus 2. 1,000,000 squared is so many times larger than just 1,000,000 that as my end behavior kicks in, I ignore every term except the leading term. The leading term is going to determine what my end behavior is. We've seen this before with odds and evens. And then you've seen it where the sign of the leading term determines in a parabola if I'm opening up or down. All right. So end behavior is determined by is controlled by the leading term of the polynomial. That tells us the degree of the polynomial and the sign. So what is the leading term of j of x? Okay. So this is where we have to get a little creative. Okay. So if this is j of x, only thing I care about is that leading term. So what I'm going to do is I'm going to just trying to hunt down that leading term. 2x plus 1 all squared. The leading term, if I multiply 2x plus 1 times 2x plus 1. That leading term is going to be 4x squared, right? 2x times 2x is 4x squared. Everything else is either going to be the first power of x or a constant, right? So what I'm going to do is I'm just going to ignore the constant term, and I'm just going to take the x, whatever the term is with x in it, and raise it to the power. In the next one, that's negative x cubed, which is negative x cubed. In the next one, it's x squared squared, which is x to the fourth. And then in the last one, it's 3x. Okay, so if I multiplied all of these out, my first, this product, or the 2x plus 1 times 2x plus 1 would have a leading term of 4x squared. This would have a leading term of negative x cubed. This would have a leading term of x to the fourth. And this would have a leading term of 3x. So if I want to find the leading term, I need to multiply all of those leading terms together. 4x squared times negative x cubed times x to the fourth times 3x. Okay, so let's go after the coefficient first. So 4 times negative 1 times 1 times 3 is negative 12. The degree of the polynomial, I'm multiplying with the same base, so I add the powers. So 2 plus 3 is 5, plus 4 is 9, plus 1 is 10. All right, so I have a leading term of negative 12 x to the 10th. So what does that mean? That means the parabola opens, or sorry, it's not a parabola. It does a bunch of other weird stuff in it. But as x goes off to positive infinity, I'm taking that massive number and then multiplying it by 12. So as x gets larger and larger, y tends toward negative infinity. What about happens as x gets more and more negative? What's happening? Okay, negative 1 to the 10th is 1. Negative 10 to the 10th is 100. Whoa, no, sorry, way more than that. Yeah, so if I continue to go negative as far as I want to, but then raise it to an even power, all the negatives get multiplied out. And then what am I doing? I'm completely run by this leading term. So as x gets more and more negative, y does the exact same thing, and it tends toward negative infinity. What does that look like on a graph? This right here. As x grows, my function is diving for negative infinity. As x gets more and more negative, my function is diving toward negative infinity. Okay, so when we talk about end behavior, this is what we mean. Right, after all the fun stuff happened, after all the intercepts and the x-intercepts, y-intercepts, maxes, mins, all that stuff has happened, the end behavior is going to run the show. Okay, so there's only 4 ways end behavior turns out. It's either both of them go positive infinity, both of them go negative infinity, one goes to positive, the other goes to negative, or one goes to negative, the other goes to positive. So there's only 4 ways this goes. All right. So there's my end behavior. My degree is 10, which again, only thing I'm worried about that is that it's even. Because it's an even degree, both tails, both ends are going to do the same thing. It's either going to be, it's just which direction are they going in. If it's an even degree, then they both either go to positive infinity or negative infinity. That's determined by the sign of leading coefficient. If the degree is odd, one's going to go to positive infinity, one's going to go to negative infinity, and which one does which is controlled by the sign of leading coefficient. All right. So let me make you a small little table right here and show you what I mean. Come on, I just want some lines. All right, so and let me give you one more piece here for notation's sake. They would say for this that the degree is 10 and that the leading coefficient, which they're going to label as a sub n, is negative 12. Okay. So now I said end behavior has 4 outcomes. So the degree d, and then I have the sign of leading coefficient. If the degree is even, I said they're either both going to point up or both going to point down. A is greater than 0. My end behavior is going to look like that. Right? All the interesting stuff happens there in that little gap. If my leading coefficient is less than 0, I still have an even degree, so that means they both do the same thing. Why is that? Because when I raise a very large number, a negative number, to an even power, the result is a positive number. Right? So that's why whenever you see this symmetry when the degree is even, because it goes to the positive infinity over here, and then it does the exact same thing over here, because the fact that it's even removes, it just eliminates that need. D is odd. Well, if the degree is odd and my leading coefficient is greater than 0, as x grows, my function grows. Okay, and as x goes toward negative infinity, my function dives to negative infinity. Right? And why does it do that? Because when you take a negative number and you raise it to an odd power, the result is still negative, right? Negative 3 squared is 9. Negative 3 cubed is negative 27. Negative 3 to the 4th is 81. You see how the odd ones, negative 3 to the 5th, negative 343. You see how when I take a negative number and I raise it to an odd power, I get negative numbers as my output. When I take a negative number, I raise it to a positive power, I get a positive output. That's what controls this. As long as the power, as long as I'm dealing with an odd power, if I have a positive number, raising it to an odd power, I'm going off to positive infinity. If I have a negative number, raising it to an odd power, it's going to remain negative after it's raised to that power. All right. Now, what happens when the leading coefficient is negative and the degree is odd? Well, this gets flipped, right? So instead of as x goes toward negative infinity, the function now goes toward positive infinity. Why? Because now the function, now the degree, the sign of the, when you take your x and raise it to that power, that's negative, and leading coefficient's negative. A negative times a negative is positive. And then as x goes to positive infinity, my function dives toward negative infinity, because now I've got like 800 squared, or excuse me, 800 cubed, which is a very, very large number, but then that leading coefficient is negative, so it becomes negative, whatever that number is. So these are the 4 behaviors, and this is when you'll see them, right? So if you can tell me the sign of the leading coefficient, the degree of the polynomial, you'll figure out what does the polynomial, or what does this graph look like on the ends. And then with all of this information, you'll be able to plot all of the x-intercepts and the behaviors according to that. All right, so let's take what we just said and use it to our advantage. Use the leading term to determine the end behavior of the graph of the functions below. Notice I'm not even going to draw. I'm not even going to sketch these, or sorry, I don't have to graph these. Okay, leading term. Leading term is the term with the highest degree of the variable. In this one, it's written in standard form. All of them are separate, so the leading term here is negative 4x to the 5th. So the 2 things I need from you are, what's the leading coefficient, and then what's the degree of the polynomial. The leading coefficient is negative 4. The degree of the polynomial is 5. All right, so the degree is odd, so that means I'm either going to be, it's going to be backwards, right? So either one's going to go to positive, one's going to go to negative, and now I just got to figure out which one it is. Okay, so take a positive number, raise it to the fifth power. That's still positive. So take 100, raise it to the 5th power. All right, that's gigantic. Take 1,000, take 1,000,000. And then when you get done, then multiply by negative 4. Well, so as x gets larger and larger, I'm diving for negative infinity. What about when x is getting more and more negative? When x is negative 10, negative 100, negative 1,000. I take negative 1,000, I raise it to the 5th, my output is still negative, right? And then I take a negative output and I multiply it by another negative number. So that means as x is heading toward negative infinity, my function is growing. Okay. Like I said, this chapter, this is why I'm doing as many videos as I am and posting stuff, because this chapter requires just practice, practice, practice. Okay. So what's next? I got 1/4 times x times 2x minus 3. Excuse me, quantity 2x minus 3 cubed times quantity 4, x plus 4 quantity squared. What is the leading term here? Now, I'm going to treat this one like I did before. Leading term. Okay. So what is it going to be? Well, it's going to be 1/4 times x times the leading term of 2x minus 3 cubed is going to be 2x cubed. The leading term of x plus 4 squared is going to be x squared. Is everybody okay with that? This took me a long time to kind of realize, even in my own experience, and it's still a difficult thing to try to teach, but each one of those terms, each one of those factors has a leading term. And if you can just multiply the leading terms, you'll find the leading coefficient, or you'll find the leading term of the entire polynomial. So let's do our powers first. That's 1/4 x. 2x raised to the third is 8x cubed. X squared is x squared. And now put them together. 1/4 times 8 is 8/4. X times x cubed times x squared is x to the 6th. 8 divided by 4 is 2. All right, so leading coefficient is 2. The degree is 6. So degree is 6. This is even. So yes, you add the powers. You add the powers of the variables. So degree is 6. So that means I'm even. So I'm either both going to positive infinity, both going to negative infinity. That is controlled by the leading term, or excuse me, leading coefficient, which is a positive 2. It does look weird because it looks like it should be 5, but remember this x right here is x to the first. Yeah, so 3 and 2 is 5, but then you got to add that one in there too, which makes it 6. Yep. So even and leading term, or excuse me, leading coefficient is positive. So what's my end behavior look like? Looks just like that. All right. So get some more examples in here. I know that, and I posted all the notes for chapter 3 as well today, so you have access to everything. I know this chapter feels like it's just example after example after example, and that's because it has to be, because we have to do so many of these to make it make sense, or to just get you practiced, get you practicing. Leading term here, negative 0.3x to the 4th. Leading coefficient, negative 0.3. The degree is 4. So degree is 4. So that means I'm either going to be like this or like this, right? Either both are up or both are down. What determines which one it is the sign of the leading coefficient. In this one, the sign of the leading coefficient is negative. So that means I can't go to positive infinity because I'm taking in some large positive number, raising it to the 4th power, and then multiplying by a negative, which is going to make it dive for negative infinity. All right, so what's my end behavior? It looks like that. And then lastly, g of x. We're going to take all the leading terms and multiply them. Notice I still take the coefficient, even though that 6/7 isn't multiplied by anything. I still use that because it's still going to be part of that leading term. X minus 9 to the 4th. Leading term there is going to be x to the 4th. X plus 4 squared. X squared. X squared. And then 3x minus 5. 3x. Multiply it all together. 6/7 times 3 is 18/7. X to the 4th times x squared is x to the 6th. X to the 6th times x is x to the 7th. Leading coefficient, 18/7. Degree is 7. Now, the degree is 7, which means it's odd. So I either have in behavior that looks like this or in behavior that looks like this. Which one is it? Okay. Well, the leading coefficient is positive, right? So if I take a very large positive number and I raise it to the 7th power, right? If I take a large positive number, raise it to the 7th power, then multiply by a positive, that number is going to stay very, very large. If I take a negative number, I raise it to the 7th power, the output's still going to be negative, right? So negative, and then multiplying by 18/7, it doesn't flip or change the behavior, it just makes it even more negative. So this is the one. Okay. Leading terms. Good. All right. So what's next? Determine the zeros and the multiplicities for the given functions. I got m of x is equal to 1/10 times x minus 4, excuse me, quantity x minus 4 squared times quantity 2x plus 5, quantity cubed. What are the factors of this problem? 1/10 is a factor. X minus 4 squared is a factor. And then 2x plus 5 cubed is a factor. All right. Now, so what do they want? They want zeros. Okay. So literally take your factor, set it equal to 0, and solve. 1/10 equals 0. Does that make any sense at all? No. None. Right? Of course, it doesn't have a 0. It's just a constant. But I want you to understand I'm taking all the factors, setting them up in the table. What makes my second factor 0? 4. What makes my third factor 0? -5 halves. Okay. So now I've found my zeros, and then I want to find the multiplicities. TIPLICITIES. Okay. So multiplicities, the 1 to the 10th doesn't have one. The next one does, though. X minus 4 squared has a multiplicity of 2, which is even. And then 2x plus 5 has a multiplicity of 3, which is odd. Okay, and notice they didn't ask for anything else. They just said zeros and multiplicities. N of x is equal to x to the 4th minus 2x squared. Now, in that form, I can't see any zeros because I don't have my polynomial is not a bunch of factors multiplied together. It's just x to the 4th minus 2x squared. There's not a bunch of stuff multiplied. So it would help to write this as 2 or 3 things multiplied together. Whenever you get a problem like this, take a look and see if there's any factors all the terms share. In this case, they do. X to the 4th and x squared and 2x squared have an x squared in them. So I can write this as factor out the x squared, and x to the 4th divided by x squared is x squared. -2x squared, take out the x squared, and I'm still left with the -2. Can I do this now? Yeah, factors. What are my factors? My factors are x squared and x squared minus 2. What are the zeros? Well, take x squared, set it equal to 0, and solve. I want x by itself. Square root of both sides. X equals 0. And then x squared minus 2 equals 0, which means x squared is 2. And now I want to take the square root of both sides. But remember, when I do that, I have to show respect and give you the positive and negative square root of 2. Okay. So those are the zeros. And what are the multiplicities? Okay, this one feels like a tricky question here. X squared has a multiplicity of 2. X squared minus 2, you may think it has a multiplicity of 2, but the multiplicity is the power that the entire factor is raised to. And in this problem, the entire factor is raised to the first power. So that is a multiplicity of 1. All right. No questions so far? Everybody okay? All right. Then let's sketch. Good. Good. All right, so let's sketch g of x is equal to -1/10. Yeah. -1/10 times quantity x minus 1, closed quantity times quantity x plus 2, closed quantity times quantity x minus 4, closed quantity squared. So what can I do with this? Let's find our zeros by breaking up the factors. I'm not going to write the constant, or actually, yeah, let's do this first. So let's just write out what are the factors that have an x in them. X minus 1, x plus 2, x minus 4 squared. All right, zeros. X plus 2 is 0, x equals -2. X minus 4 equals 0, x equals 4. So that's 3 zeros. Okay. And then what are the multiplicities? Power that they're raised to. If there's no power, it's always understood to be a 1. So this is a power, this is a multiplicity of 1. Second one has a multiplicity of 1. And then the last one has a multiplicity of 2. All right, so what does that mean? That means if I go to my graph, I can plot all of these. 1, 0, -2, 0, and 4, 0. All right. What else can I find? I can also find the y-intercept. Yes, you can. You can just plug in numbers. What's the y-intercept of this original function? Okay. Well, I just plug in 0 for x and see what happens. That's -0.1 times 0 minus 1 times 0 plus 2 times 0 minus 4 squared. -0.1 times -1 times 2 times 16. -4 squared is +16. What happens when I multiply this? let's see here, 1/10, negative 1/10 times negative 1 is positive 1/10. Positive 1/10 times 2, positive 2/10, positive 2/10 times 16 is what? Negative times a negative is positive. So I'm looking at a y-intercept of 3.2. So 0, 3.2. So I should be here. So I've got my zeros graphed. I know the multiplicity. The only thing that's left for me to figure out is the end behavior. All right, so let's see, what's the leading term? Leading term is negative 0.1 times x times x times x squared. X times x times x squared is x to the fourth. So that's negative 0.1 x to the fourth. So that means I have even degree. Leading coefficient is negative 0.1. The degree is 4. So that means what? I'm either up both ways or down both ways. Leading coefficient's negative, so it means I'm doing this. All right. So the end behavior helps me know where to start my graph and then where to end it. If you want to plug in some more points, you can absolutely do that. But what I want to do is just kind of manipulate the problem as it sits. So what have I got? I'm coming up from negative infinity. And when I get to negative 2, whoop, that's not a function if I draw it that way. So here is, I get up here to negative 2, and that has an odd power, odd multiplicity, so that means I cross. Okay, so I come up, I get to my y-intercept, I come down, and when I reach 1, that has an odd multiplicity. So that means I cross again. And then I've got to come back up and catch this last x-intercept. That has an even multiplicity, so that means I touch. And that's my sketch. Again, as I've said many, many times, there's a reason I'm telling you to sketch and not graph. Okay? I want you to put your best effort up there, but if I wanted an actual graph, there's 1,000 ways to do it that are easier than this. Okay? What I want you to start to understand or see is how everything we've done this semester has kind of led us to, we know how to find x-intercepts, we know how to find y-intercepts, we know how to deal with end behavior, so now I'm putting all of that together. All right. Lastly, sketch the graph. Let's skip that. I'll put this on the video for next time. I'll finish this up and post it as well. I want to get into 2-3 because it is a long section, and